Hi friends, welcome to our channel. Here we are going to look at this problem, number of ways to arrive at destination. This is a graph problem. So this graph problem, and we are going to solve it using Dijkstra's algorithm. Plus dynamic programming. So I can see some dynamic programming ingredient, right? So with that said, let's quickly look at the problem statement. So basically, we are given a weighted undirected graph or bidirectional graph. So here we want to find the number of ways we can arrive at our destination in the shortest amount of time. So also we need to modulo this answer by a big prime number. So 10 to the power 9 plus 7. So this is a big prime number. So let's just make this comment here or remark. So before we solve this problem, let me give you some background. So for this kind of problem, the shortest path. So first you can think of BFS, right? So this is the one can be used to solve some shortest path problem. This is the one. And then here for this flavor of problems, you can also think of another three more advanced algorithm. Three more advanced algorithm. So here by advanced, still I feel that they're all very classic. So one is so Bell method, right? So you can try this method. So this is a single source shortest path algorithm. Another one is Floyd-Warshall. So this is the all pair shortest path. Shortest, not shorted, shortest path algorithm. Another one is the one we are going to use is called Dijkstra's algorithm. So this is a single source shortest path algorithm. So we're going to use this is here. We're going to use what we use, right? So before we look at the implement the coding, so here let's quickly look at the constraints. First, here the number of nodes is bounded above by 200. It's not very large, and this is the weighted graph, right? So the time is in this range. UI does not equal to VI, no self path, right? So there is at most one road connecting any two intersections, and you can reach any intersection from any other intersection. So these are important additional assumptions. Some are consistency requirements, some are size constraints. So with that said, I guess we are ready to do the coding. So if you are familiar with Dijkstra's algorithm, so let me copy this one. So there are two ingredients in this algorithm. Two ingredients. So one is a heap, right? Priority queue. You can also a heap data structure. Another thing actually appeared in Dijkstra's algorithm is the so-called relaxation, right? So if you know or you can remember these 2 points, basically you can run a working Dijkstra's algorithm. But here an extra point is that we want to find further the count of shortest paths, right? So in other words, so there might be different routes, all from the source to the destination have the minimal time, right? That's what we want to find. So in other words, so you need to know how to find the shortest path using Dijkstra's algorithm, and in between you need to know how to do the counting, right? So with that said, let's look at the coding. So I'm going to explain the detail in the coding with some certain detail. So first, I'm going to use adjacency list, right? This is rather common, right? So we have a graph. So here, I'm going to, for say a dummy index in range n. N is a number node. So for each node, I'm going to represent that using index. So each index now is assigned a empty list. So the empty list are going to hold what's going to hold? It's going to hold the neighbor and the time between this index node and the neighbor, right? So with that said, let's traverse the road. So for u, v, and time, right, in rows, what we're going to do is graph u. So notice that here I'm using list, so I'm going to use append, right? So I'm going to append, from u to v, we need time, this time. So this u, the node, and then to the neighbor v, it takes time, right? So similarly, because it's undirected or bidirectional, you need to do the reverse. So here is u and this time, right? So this finishes the build of the graph. So now let's prepare for Dijkstra's algorithm. So here I'm going to have one list. So this you can use dictionary or you can use list. So each element means the shortest distance from source to this corresponding index node. For example, 0, and it's just 0 we are going to set. So, so this is the one. And also the number of ways. So originally we initialize as 0, right? So now we know the source, right? We know the source will be the 0. So we are going to send the list from 0 to 0 will be taken 0 time. And the number of ways arriving at 0 from 0 is 1, right? So in other words, ways is the number of time from the source to a certain index node. For example, if your index in this list is I, it means the number of ways from the source to the index node. So this is a preparation. Also, we need a priority queue. So here, I'm going to use this 0 and 0. So here, the priority queue or heap is going to store the distance from the source node to the current node, and this is a node, right? So originally, your node to be considered is 0. So from 0 to 0, the time is 0. So you can understand it as distance or time. So I'm going to use it interchangeably, right? So now we have this. And also we know that by requirement, we need to modulo this large constant or prime. So we can use this plus 7. Let's just make it a constant, right? Just for bring us some convenience. So now it's the major while loop for Dijkstra's. So what we are going to do is, the priority queue. So we are going to do some pop operation. So we get the current distance or time. So this will be heap queue, heap pop from the priority queue. So then what we are going to consider is if D is greater than this node. In other words, so this distance singly is just larger than the current shortest distance from the source to this node. Then we continue, right? We don't consider this possibilities. The reason is that this will not yield shortest path for sure. So then what we're going to do is for, because it's the way of writing, so we actually entering, you can think of we entering the if block. So basically for neighbor and time in graph node. So in other words, we examine this edge. So between node and neighbor, right? So then we want to check. So here is relaxation, right? So what we do is if this node plus time is less than this neighbor. So this is important. It means that if we arrive at the neighbor by way of the node through this edge, node to neighbor, so it yields a shorter time or shorter path, then we are going to replace that. This neighbor is going to be this one. So notice that this is the relaxation, but we also want to count the ways. So in this case, because we just reset that, so the ways of arriving at the neighbor equals the ways arriving at this node, because we consider the node from neighbor, this is just one path. Then by multiplication rule, you just one multiply this ways of node, right? So this is the one. And also don't forget to do heap operations, heap kill, heap push. So push priority kill to priority kill, and then this information, this neighbor and neighbor, right? So this is the one. Another case is that if this were the same, so in this case, what we are going to do is that we don't update the distance, rather we update the ways. So neighbors, actually it's incremented by ways of a node, right? But we want to do this modulo operation, so we write like this. So it equals the ways of neighbor plus ways of node. Then actually we do this modulation operation mode. Let me here add open parentheses. So that's it. So because here we don't, this is not relaxation, right? Because it's just for counting. So then what we do actually is afterwards we are going to return with a-1. This is the destination. So this actually basically is a full implementation for this problem. So now let me first run a test to see. Here not right. Let me check that. So here we have this UV time enrolled, UV time, VU time. This is right, and then this is also right. Float infinity, right? So here we set this to be 0 and the ways to be 1, and the priority queue to be this one. And then let's look at this one. D node is pop, and then if D is greater than this one, we're going to continue. Otherwise, for neighbor in graph node, so if this one is less than this neighbor, we're going to do neighbor node plus 10. Then neighbor ways is this also right. And then otherwise, this one is, so here I copied this one. It should be equal, right? So if they are the same, right? That's actually the same. Now let me run it again. Yeah, it passes the two cases. So now let's look at the generic case. Yeah, let me run it again. Yeah, it should be very fast due to the introduction of priority queue. So with that done, I guess it's time to make some comments. First, this Dijkstra's algorithm. There are two major ingredients. One is a heap data structure or priority queue. Another one is the relaxation operation, right? So if you notice these two ingredients, in general, you can write a working Dijkstra algorithm for shortest path problem. So here we also have a counting, right? So essentially here we are doing dynamic programming. So you can write ways as DP, right? To emphasize that point, but we didn't do that. So this is the first comment. The second comment is that here we are using the if and else if block. So if you just want to find shortest path, you don't need this else if block, and also you don't need the ways, right? But here, because of the counting, we have this one. And also this is very important, because if they are taking the same time for different routes, this is exactly what we are going to count. So this is the second comment. the third comment is coming back to the original beginning. So for this kind of problem, depending on the problem statement or problem logic, first, I guess you need to try breadth-first-based traversal to see if you can solve the problem there. Otherwise, you can think of Bellman-Ford algorithm and Floyd-Warshall and the Dijkstra algorithm. Actually, I saw some problem in LeetCode, so you can solve using Floyd-Warshall, because this algorithm is essentially in cube, where n is the number of nodes, right, in time complexity. But also for this problem, you can also try Bellman-Ford, right? So with that said, I guess that's the 3 comments I want to make. Meanwhile, we have a playlist on graph problem in our channel. You are welcome to try that problem. Oh, I guess I forgot one thing. So here, actually, I'm using list. So you can let me copy this one and make some tweaks so that you can have another choice. So you can also use default dictionary. So here, let me see. I can change this to V, and here actually you can do this. You can use collections default dict. So I'm going to set a callable, let's say, set, or you can think of this container as an empty set. So then what you do here, because it's set, you can do add, right? You can do add. So essentially the same. Now you can run it. Submit that. Same thing. So again here, if you like, you can also translate this with and so let's see this. So I can translate to be a and also a dictionary. So let's see, collections default dict. So here I can first map everything to be float to infinity. This is the one, and the ways I can use counter, right? Collections counter, right? So by default, counter will set everything to be a 0 at first, so you can run it. Yeah, it also works. So with that said, I guess that's about it. So the first way might be the preferred way if I wrote the solution. I guess the video is already too long. I'll stop here. Thank you for watching.